Okay, let's dig into this. Imagine your body, right? Not just organs and systems, but think of it like a grand living building. And deep inside, holding it all together, there's this hidden scaffolding. It's called the extracellular matrix, or ECM for short.
Uh-huh. It's absolutely crucial. It gives your tissues their form, their strength, their bounce back. And it's how cells talk to each other, really.
But here's the thing. Just like an old building, the scaffolding, well, it doesn't stay perfect forever.
Exactly. As we age, it starts to get stiff, less flexible, harder for the body to maintain.
And the main reason for that stiffening is something called cross-linking.
Right. Think of tiny chemical bonds forming between the proteins in the matrix, bonds that shouldn't really be there.
They kind of gum up the works over the decades, making everything rigid.
There's one specific culprit scientists are really focused on now: glucosepane.
Glucosepane, why that one in particular?
Well, it's complex, it's incredibly stable, chemically speaking, and it really builds up deep inside collagen, which is a major ECM protein.
So it's stubborn.
Very stubborn. There are other cross-links, sure, like pyridinium and pyrrole, but glucosepane is kind of the big one for aging research because it's so prevalent and hard to get rid of.
Okay, so if this stiffening is such a big deal in aging, why haven't we fixed it before? What were the roadblocks? Was it just we didn't have the right tools?
That's a really good question. For a long, long time, the challenge was precision. How do you target these tiny, specific, unwanted bonds?
Especially when they're deep inside tissues.
Exactly, without damaging all the healthy stuff around them. There was a drug maybe 15, 20 years ago, ALT-711.
Oh, I remember sharing about that.
Yeah, it showed a little promise. It seemed to loosen up some types of crosslinks.
But not glucosepane.
Nope, couldn't touch
Nah.
glucosepane. The analogy I like is trying to remove a single deeply rusted bolt from a huge ancient cathedral.
Without cracking the stonework.
Precisely. You need tools with incredible, almost atomic level precision. And that's something we just didn't have for this specific problem.
Until maybe now.
Well, that's the hope. The new angle is coming from the digital world, artificial intelligence.
AI, not just for chatting online, but for designing molecules.
Specialized AI, yeah. Systems designed specifically for enzyme design.
Okay, enzymes. They're nature's catalysts, right? They speed up specific chemical reactions.
Exactly. They're incredibly specific. So the idea is, can we use AI to design a new enzyme? One that's perfectly shaped to find glucosepane and just SMIP it.
Cut that specific crosslink.
It's a huge challenge, designing enzymes for jobs that nature, never evolved them for.
But AI might give us a shot because it can process way more information.
That's the potential game changer. AI can explore possibilities, chemical shapes and interactions on a scale that's just impossible for humans or traditional methods. It's moving from trial and error to, predictive design.
Okay, so that's our mission for this deep dive then. We're exploring how AI could potentially help us fix this aging scaffold, this ECM, by going after glucosepane.
We'll look at the tools, what progress is being made, and, what this could actually mean for your health down the line.
Right. So let's go a bit deeper into the ECM problem itself. We said glucosepane makes it stiff, but how does that really mess things up? It's not just about feeling less flexible, is it?
No, not at all. Because the ECM isn't just passive scaffolding, it's active. It influences cell behavior, tissue repair.
So when glucosepane builds up deep in the collagen fibers, it changes the whole environment.
It fundamentally alters the mechanical properties, the signaling, everything. And this happens in tissues all over your body.
And for ages, we just couldn't really do much about it.
Pretty much. The tools weren't there. But now AI is stepping up, like a molecular apprentice, learning how to build the tools we need.
So what are some of these specific AI tools? You mentioned enzyme design.
Yeah, there are systems with names like meta-enzyme and enzygen.
Okay, what do they do?
Think of them as AI that learns the fundamental rules, the grammar, if you like, of how enzymes work, their shapes, their chemistry.
Based on studying thousands of existing enzymes.
Exactly, from massive biological databases. And by learning those general rules, they can then try to predict new enzyme structures.
Structures that could bind to and break something unusual, like glucosepane?
Designing a key for a lock nature never actually made.
That's pretty amazing. Does this connect to other AI drug discovery stuff we hear about?
Absolutely. It shows the broader potential. Take, for example, Neuritis. They have something called PepRTE62G, or PepTiYouth.
PepTiYouth, what's that?
It's an AI-discovered peptide, a small protein fragment. Now, it's not a cross-link breaker, let's be clear.
Okay, different target.
Right. But it reportedly helps stimulate your skin to produce more collagen and elastin.
So aimed more at skin health, maybe cosmetics.
Potentially. The key point is it shows AI can rapidly sift through possibilities and find these bioactive molecules much faster than traditional methods. Now, public info suggests it's still early days lab tests, maybe some limited human testing. Needs more proof, definitely.
Sure, needs verification. But it's a proof of concept for AI speed in finding useful molecules.
Exactly. It demonstrates the power of the approach.
But back to glucosepane, finding the molecule is one thing. Making it real, testing it, that's the next hurdle.
Oh, absolutely. An AI design is just a blueprint. You have to build it and see if it actually works in the real world, in the lab.
And are we seeing progress there?
Yes. Crucially, there have been a couple of key developments that make testing possible.
Okay.
First, glucosepane synthesis. Researchers, I believe, at Yale figured out how to actually make glucosepane in the lab.
Create the target molecule itself. Why is that so important?
Because you need a reliable supply of it to test your potential breakers against. If you can't make the lock, how do you test the key?
Right, got it. You need the problem molecule readily available.
It's a fundamental step. Without synthetic glucosepane, progress would be incredibly slow, almost impossible.
Okay, that makes sense. And the second development?
Well, there's a biotech company out there, Pharmaceuticals. Reports suggest they are, or at least were, actively working on developing glucosepane-breaking enzymes.
So a dedicated effort.
Seems like it. Now, it's important to say, this stuff is usually early stage. Biotech focus can shift, but it indicates that people are seriously investing in cracking this specific problem.
Okay, so we have AI designing potential keys, we have the synthetic locks to test them on, and companies trying to build those keys. How does this realistically play out? What's the path forward?
It's definitely a step-by-step process, a phased approach.
Right.
First, the design phase. AI proposes enzyme candidates that look like they should bind to glucosepane and cut it.
The blueprint stage.
Then testing. Lab experiments. Does enzyme X actually break synthetic glucosepane in a test tube? Is it specific?
And if it works?
Then comes refinement. Can we make it more stable, more precise? Crucially, is it safe? Does it damage other things?
That safety part sounds critical.
Absolutely paramount.
Yeah.
And only after all that, you move to translation, trying it in animal models first, see if it works in a living system.
And eventually, if all goes well, human trials.
That's the long-term goal. But it's a long road. And it's really important for people listening to understand the first realistic target, if this works, would almost certainly be glucosepane alone.
Just that one specific crosslink.
Yes. Tackling other types of crosslinks, like pyridinium or others, would likely require developing entirely new enzymes, probably much later, assuming the glucosepane approach proves successful first.
Okay, so focus is key here. Now let's connect this back. Why should you, listening at home, really care about glucosepane and ECM stiffness? It sounds technical, but what's the real-world impact?
Well, it goes way beyond just, wrinkles or feeling a bit stiff. This ECM stiffening is implicated in some really serious health problems. Such things like cardiovascular disease, stiff arteries, raised blood pressure, kidney decline, the filtering units get stiff and less efficient, lung stiffness, making breathing harder. Even things like reduced skin elasticity are linked back to this matrix stiffening.
Wow. So it's not just cosmetic aging at all. It's fundamental to how well multiple organs work as you get older.
Precisely. So tackling ECM stiffness, specifically glucosepane, isn't just about treating symptoms of these diseases. It could potentially address one of the root causes of age-related decline across many different body systems.
That sounds profound, like fixing the foundations rather than just patching the walls.
That's a good way to put it. But, and this is really important, it wouldn't be a magic bullet that replaces everything else.
Right. You still need to worry about mitochondria, inflammation, stem cells, all the other aspects of aging we talk about.
Exactly. Think of ECM rejuvenation, if it becomes possible, as one crucial piece of a much bigger puzzle.
A new tool in the longevity toolkit, basically.
A potentially very powerful tool, yes. Adding to, not replacing, strategies for healthy aging.
So, summing up then, where do things stand realistically?
Well, we need to be honest. ECM rejuvenation using AI-designed enzymes is still, quite speculative.
It's not happening tomorrow.
Definitely not. It needs years more research. There are huge technical hurdles, safety questions, regulatory pathways to navigate. It's complex.
Cautious optimism is probably the right phrase.
I think so. But the exciting part is, for the first time, we actually have tools these AI systems that seem capable of imagining the solutions.
Tools that can design those molecular keys we talked about to potentially unlock the body's stiffening scaffold.
AI is giving scientists a much, much sharper chisel than they ever had before for this kind of problem.
So while time inevitably leaves its mark on all of us, maybe, just maybe, these kinds of advancements could one day help us restore some of that youthful suppleness to our biological architecture.
Keep the cathedral standing strong for longer. That's the hope.
A fascinating prospect, definitely something to keep an eye on.